Hello everyone! We need to now take a look at the new unit which deals with kinetics and equilibrium. So far we know that reactants will react to make products. Okay, we know that there is a certain amount of energy that's associated with them. That's what we learned in our thermodynamics unit. And now we need to know, when is a reaction actually going to take place? Okay, you think, oh, I got a couple of reactants, I'm going to stick them together and they're automatically going to react. That, my friends, is not the case. So let's take a look and see what needs to happen in order for a reaction to take place. Okay, so the first thing we're going to look at is something called collision theory. Postulate number one of collision theory states that molecules must collide in order for a reaction to occur. Now, I know that seems very basic. Obviously, molecules have to collide. But if I were to take these molecules in this and these molecules in this and try to get them to react, okay, are they going to react like that? No, of course not, because they can't touch each other. Okay, so I've got to actually squeeze that in there in order to potentially get a reaction to occur. Okay, secondly, they must collide with enough energy. Okay, if a couple of molecules are coming at each other and then, no, they don't collide with enough energy, they are not going to cause a reaction. Okay, so what I mean by that, we talked in the thermodynamics unit about how you have to get up to the top of the hill. Okay, you've got to make the activated complex, and that energy that's associated with that is called the activation energy. So when molecules collide, they have to collide with enough energy to make it to the top of the hill. Okay, if they get to the top of the hill, then they'll roll back down the hill and form their products. Okay, and of course, we already know that the difference between products and reactants is known as enthalpy. Okay, the third part of collision theory says that when molecules collide, they don't just, it's not just that they have to collide. It's not just that they have to collide with enough energy. They also have to be facing the right direction when they collide. Okay. So if you got a molecule that looks like this and a molecule that looks like this, okay, they have to collide appropriately in order to cause a reaction to occur. Okay, if one of them's backwards, then it's just going to bounce right off. Okay, so that's the third part of collision theory. Molecules must collide in the correct molecular orientation. Otherwise, they'll bounce off and they'll find another molecule to react with. Okay, once they find one that they can collide with enough energy in the correct orientation, then they'll have a reaction. Okay, so it says in summary, they got to collide with enough energy in the correct orientation. What, my friends, can we do to speed up a reaction? Well, there are multiple things that we can do. Number one, the first thing that leads to how fast a reaction is going to go is the type of the reaction. Okay, we're going to spend a little bit of time on this one. We know that if I take a drop of one thing and a drop of another thing and they change colors real fast, okay, that reaction went pretty quickly. Okay, that's generally going to be your double replacement reaction. And the reason that those are so fast is because, remember how we talked about way back when we talked about reaction types, we talked about redox reactions. Okay, and when you have a redox reaction, essentially you are shuffling around electrons and you're changing the oxidation numbers of things. Okay, when that happens, there's a lot that goes into that. Okay, and so therefore, when you have a redox reaction, that reaction is going to take place slower than a double replacement or a non-redox reaction. Okay, so this is already something we've already seen. Okay, remember that the gain of electrons is called reduction. Oh, what? Gain? We gain to reduce? We're reducing the charge. Okay, the charge is going down. The charge is going to become more negative, and oxidation is the loss of electrons, and um, therefore our oxidation number is going to get larger. Remember the saying, Leo, the lion, says grr. Okay, we've already done this one once, so this stands for the loss of electrons is oxidation. The gain of electrons is reduction. Okay, and remember that goes for that when we're talking about reduction, we're talking about the reducing of the charge, not the reducing of the number of electrons. Okay. Let's see here. It says in the synthesis of iron to sulfide from iron and sulfur, what is oxidized and what is reduced? Okay, well, let's do the problem. Fe plus O2 yields iron to sulfide is just FeO. Remember, when you have elements that are by themselves, they're not part of a compound, they're going to have an oxidation number of 0. Okay, when they're in their compounds, then their oxidation number is going to be what's matched on the periodic table. Okay, so iron, since it has a Roman numeral 2, that tells us its oxidation number is plus 2. Oxygen has a oxidation number always, since it's in group 16, of negative 2. So iron went from 0 to negative 2, or excuse me, to positive 2. Okay, so I know that my charge went up, so my number of electrons had to go down, right? My charge goes up to plus 2, so therefore I lost electrons. So we would say in this case that iron was oxidized. Okay, oxygen goes from 0 to negative 2. My charge goes down, therefore my number of electrons had to go up, so I gained electrons. So we would say that oxygen was, if I can find my pen cursor, where are you? There it is. Oxygen was reduced. Okay, that's how you do it. Let's see here. Let's look at this. Which of the following would be considered a redox reaction? Well, I've got 0 and 0 going to plus 2 and minus 1 because it's plus 2. Magnesium's plus 2 because it's in group 2 on the periodic table. Bromine's minus 1 because it's in group 17. There's zeros to start off with because they're by themselves, so this one is a redox. Okay. Sometimes you only need to look at one thing. Okay, zinc is 0 here, and we know that zinc, when it's in a compound, has a charge of plus 2. Okay, or an oxidation number of plus 2. That one thing, because it changed charges, tells you that that one is a redox reaction. Now here we have a double replacement reaction. We should remember back from our reactions unit that double replacement means that it's not a redox reaction. So this one's not redox, and neither is this one for the same reason. Okay, let's stop there for right now. We'll take a look at the other factors which affect the rate of reaction on the next video. Thanks.